And greet everyone on VSA Online today. So welcome back. So today it's my great pleasure to welcome Chris Kim from UC Berkeley. And today, well, he's already traditional speaker on these webinars. So today he will be talking about oscillator associative memories. Really cool topic. So Chris, please.
Great. Thank you, Evgeny, for the introduction, and thank you so much all for being here. Really happy to chat about this work. So, if you want to read more about it after the talk, there is a link to this open review submission. So, an early version of this work was submitted to the New Frontiers in Associative Memory workshop at ICLR last year. And if you have a chance to go this year, I had a really good experience and would be happy to chat with anybody more about that. And it's also been submitted and accepted to COSIGN, which is Computational Systems Neuroscience. So I'll be presenting it there next month. So I hope that what you'll take away are some really exciting developments in tying together oscillators, HD computing, resonator networks, and some related topics. And that please stop me if you have any questions in between, as I think that I try not to give too many slides so we have plenty of time for discussion. And you'll hopefully see why the animation is playing by the end of the talk. I wanted to start things off by, for this audience, introducing compositional structure or the binding problem. So I don't think that these are the same problem, but I think that they are closely related in that we want neural representations or population codes that are able to keep track of compositional information. So for example, to associate particular objects with particular locations and with colors, and not getting red circles and green squares mixed up with green squares or green circles and red squares. You can see how easy or difficult it is to keep these things together. I think a related problem to this is the problem of factorization, which is the task of, given a particular image, decomposing it into different objects and their attributes. And interestingly, it seems like this is what the hippocampus and entorhinal cortex are set up to do. So I've taken this picture in the bottom left from Mans and Eichenbaum, which is giving you a structure of the neuroanatomy of the entorhinal cortex and hippocampus. And the key point here is not to get lost in the neuroanatomy, but to emphasize the role of factorized representations and conjunctive representations. So there are separated representations, for example, for content and context, that join together in the hippocampus. So this is a problem not just for visual scenes, but also for memory more generally. Now, it's also worth noting that in the literature on binding, there's a long-standing debate in neuroscience about whether binding occurs via synchrony. So whether or not we're able to segregate different objects, or rather that the neural code is able to, by spike timing information. So different spike times lead to different groupings, and this leads to different segmentations of objects. And there are a whole bunch of computational models that try to make good on this idea. A more recent one is this artificial Kuromoto network by Miyato and colleagues that was published in ICLR last year, where they take these ideas and use it for tasks such as segmentation, but also for reasoning problems like Sudoku. And they argue that this oscillatory dynamics is especially efficient at solving these types of problems. So this is just a bit of introduction to approach at the general problem. So now I'll introduce to you resonator networks, and I realize that for this audience, some of you have seen resonator networks and even talks in VSA Online, and then for others, it might be your first time. So let me just kind of walk you through both example and then the underlying intuitions and so forth. So the intuition is that, say we have a scene that has multiple objects in it with, say, multiple digits. In this case, this is from the MNIST data set. And we want to factor it into different objects with different components. So horizontal, vertical positions, and then the object identity, so its digit location. So if we wanted to solve this problem by brute force, then we'd be left with a large combinatorial range. Even for just one object, if there are 10 different digits and 100 possible different positions for horizontal and for vertical, then that would leave us with a search space of 10 to the 5. But it seems that the problem should be much simpler. And it is, because really underlying that are just 100 plus 100 plus 10, or 210 total possibilities, which allows us to decompose this problem. So the way that the dynamics work is that we're going to have an estimate, so for horizontal position, vertical position, and object. And remember, this is just an example, just to give you some intuition for how the algorithm works. And in order to estimate our vectors for each of these positions, we're going to take the inverse or unbinding of our other factors. So for horizontal position, it's the vertical and the object with our scene vector, multiply it by these code books or this outer product matrix to project us onto the span of the right solution space, and then repeat this until the algorithm converged. And the key thing is that Z is the product of H, V, and O for some true but unknown H, V, and O. And if we have all but one of the right factors, then inverse multiplying the other two is sufficient to divide out on both sides and get the right solution. So that at least guarantees that our network or our algorithm, if the solution is right and the dictionaries are not too large, is able to converge to the right solution if it's there. Whether or not it gets to that is a separate question. But again, just to give you some animation for how this works, and I'm just picking the one that I've personally made, but there are other versions of this that you can see. So if we have a particular digit, you can see, and we're just looking over time, the inner product to different factors within the codebooks. Then what you can see is that it's picking out one at a time. It does this by subtracting and explaining away and shifting between different digits. And it settles to particular objects and then particular positions. And yeah, the animation is now just looping. But the intuition here is that it's able to iteratively converge these right solutions. At first, it might not be very near the right solution, but through progressive refinement, it's able to converge. But the question that I want to leave you all with is, when is it going to converge? What are ways of improving the network so that we can both understand its convergence properties, but also hopefully improve them? And it turns out that the oscillator implementation has a nice solution to these stories that I'll be telling you about. Before that, I want to acknowledge that there is a lot of work on resonator networks, and there's people, including Paxson, who have done a lot of the work to pioneer these ideas, and then a lot of work in the field since to give various applications, neuromorphic implementations, and so forth and so forth. So if you've happened to see my previous talks at VSA Online, I've tried to lay out some of these connections in more detail and some of my prior work on thinking about residue numbers, thinking about grid cells, hippocampus, visual scene understanding, and so forth. So that's not going to be the focus of today. The focus is going to be on oscillations. But I think that like the main point that I want to go through is not just that there's a lot of work or prior work on like resonators and give you a list, which you can feel free to look through on your own time, but that there's a lot of really interesting and interconnected ideas that are coming from the VSA community. And I think that it's to everybody's benefit to see how these ideas are interacting with each other and what interesting ideas or contributions are coming from each of these possible papers. Some additional considerations are that there's some work on thinking about using linear codes for hyperdimensional computing by Netanel Raviv and colleagues, which provide an alternative to using resonator networks for solving a similar kind of factorization problem. And then there's work from the group at University of Waterloo, so Brent Comer, Nicole Dumont, Jeff Orchard, Chris Elias-Smith, and Michael Furlong, who have been doing interesting work tying these, again, to the brain and to neuromorphic computing as well. So even though those are not directly resonators, I think that there is definitely overlap between the sections of work. And I think that this is an exciting place for the discussion afterwards. But yeah, with this abbreviated related work section, I now want to tie us back to some other earlier work that's exciting, which I think is the new contribution, which is associative memory in oscillators. I want to initially bring this out by picking out this paper from Andre Nust. So this is Neural in Information Processing Systems, not advances in, so it's actually the first one in 1987. And so you can see this is actually the original typesetting of the paper. And the key idea here is that if you have a popular network model that has -1 and +1 values, you can think of those as a special case of a complex valued associative memory network that is quantized into two particular states. But in reality, you can also design an associative memory network such that any complex number with unit amplitude, which is called a phasor, would be a possible state that the system can take. And then you can quickly go from a discrete valued representation that has finite amplitude elements to a continuous valued version. And then we can go back to discrete. This is coming back in a few slides. And in this paper, NIST proposed a few different dynamics. So one that looks quite similar to just the Hopfield 1982 model, except that it uses complex valued units instead of -1 +1 bipolar vectors. And instead, also this continuous time parallel evolution for updating the weights. So if let's just walk through what this equation is saying. So in this case, the dynamics are on the angle of this complex valued variable SI. So SI is the ith component of some vector S. And the updates are only on the angle. So this is a very straightforward and simple way of preserving the amplitude rather than thresholding later on at the end. And it turns out that now the trick is to multiply or to add to this particular phase the sign of the difference between the current phase and the phase of what I'll call the pre-activation term, which is the contributions or the weighted contributions from all of the other units. So what happens, or one easy consequence of this, is that you'll have a fixed point if the angle of HI and SI are equal to each other, and then the network will settle to a particular solution. If you have a network where the weights are Hermitian symmetric, then this is going to descend an energy function, and so you have very nice properties as you would with typical Hopfield networks. And it turns out, yeah, these networks are very related as well to Kuromoto oscillators, which are also acting on the phase and have nice synchronization properties as well. More recently, there's been work on using these oscillatory systems for solving difficult combinatorial optimization problems, such as KSAT optimizations, which are known for the 3-SAT case to be NP hard. So one example of this are called oscillator Ising machines from Kenshi Wang and Jujit Rochaudhuri. So this paper is from 2021. They have a series of paper on this, where the idea is that you want the system to have two stable states at -1 and +1, or 0 and 180-degree phase, but with recurrent connections that define the energy states of these networks, you wanted to find the minimum energy state. And you can then map that onto specific combinatorial optimization problems. And what Connor Bybee and colleagues in the Redwood Center did is to suggest a higher order version of this Ising machine. So rather than work on second order connections between units, you can have instead third order connections, and that this is going to be much more efficient in terms of solving similar types of energy function problems in order to solve these very difficult combinatorial optimization tasks. So maybe an important point to emphasize is that it's not that there's particular magic in getting around the inherent difficulty that these problems face, but rather that the hope is that with particular types of hardware implementations or neuromorphic circuits that could be run in much more efficient form factor than current forms of computing, it will still come out to be a much more efficient solution for many problems of practical relevance. And so with that, now I introduce to you the way of combining oscillator methods with associative memory. So I'll now introduce this to say, suppose that we have a vector that we wish to factorize into two things. So S is our vector, and it's just the Hadamard product, so element-wise multiplication of two variables, x star and y star. And both of these we'll say are d-dimensional phasor vectors, which means that they're complex numbers with unit amplitude. In addition, the other assumption is that x star and y star come from some discrete set of candidate vectors. So there's a code book of x1 through xm, let's just say, that these vectors could have come from. This means that a discrete search may be very inefficient, but at least it would guarantee the optimal solution because there would be one exact match for this particular choice of candidate vectors. So now the goal is to say, given S and our knowledge of the set of candidate vectors, or the codebook, evolve estimates of phi x and phi y that converge to x star and y star. So the idea is that because the only relevant variables in x star and y star are in fact the phase, we just want the phase vectors to match x star and y star. In practice, there's going to be one degree of freedom, which is that we might be off by a constant phase shift for one variable and the anti-phase shift for the other variable, and it'll still multiply out to be the right vector. But the fortunate feature is that if we're looking at complex valued inner products, we just care about the amplitude of that complex valued inner product rather than its real or imaginary component. We would care about the real part if we wanted them to be exactly aligned, but there's fortunately a nice way to be able to check this. So now the dynamics are going to be very similar to what we saw from the Nost model and then from the resonator network. So recall we had our dynamics where we had sine of some pre-activation term and then the current phase. Again, so this term, it looks exactly the same. So we also have these dynamics that run on the phase for both x and y for each of the components. But now in this h term, this pre-activation term, we have a multiplication, in this case for the x variable y. So this is inverting the estimate that we have for y. And then for y, we're inverting the estimate that we have for x. And then we multiply it by this matrix A, where A is formed by an outer product learning rule, formed by creating an outer product of each of the different code words or candidate vectors for each possible set. So now what we have is a system that is implementing resonator network dynamics, but instead of doing hard thresholding, where we take a matrix multiplication, get some phase and amplitude for each of our individual components, and then normalize that phase back to 1. The phase is always going by 1, is always 1 because the dynamics are just evolving between for either advancing or delaying the phase. And yet it's able to converge to particular solutions. So now I'll tell you about why this solution ends up working better than the discrete versions, which are, again, solving a similar type of objective, but doing it with different dynamics. So the first thing is a simple experiment to see if we look at the number of patterns per module. So this is m. And in this case, we just have two factors. So the total search space is m squared. And then look at the capacity as we increase the number of patterns per module. So as is seen by previous papers, for example, from Paxson and Spencer, we've noticed that the accuracy, it starts off at 100% when there's not very many patterns. And then as the number of patterns increases, it goes from 100% and then gradually decays. But the key thing is that not just that as you increase the dimension, you're going to have a larger range at which the accuracy stays high, but also that regardless of the dimension, the continuous time version, or I've called it FOAM just as a catchy acronym for Factorized Oscillator Associative Memory, is able to do better than the baseline resonator network, even when the setups for the problems are otherwise the same. So the reason for this is the underlying dynamics. And the main claim is that, of course, the capacity falls off at a certain point. The accuracy is going to be decreasing. But at the same time, there is a range at which the accuracy stays high for the continuous oscillator version, but is lower for the baseline resonator network. So why might that be? So one reason for this, or that's pointed out in the original set of resonator networks paper, so I've taken this from Spencer Kentedal, Resonator Networks 2, is that as you increase the search space size, the accuracy starts to decrease when the number of iterations goes up. So it seems that, at least this is the reporting from the original paper, that the resonator network is falling into these limit cycles in which it has failed to converge. And so there's been a lot of work in the prior literature to think about why might that be, what are solutions to address it, and so forth. But I want to leave that as the initial diagnosis for what's going on when this convergence is happening. So in order to investigate what might be the difference that's accounting for this empirical increase in the performance, what I did was to look at different variations, so different pattern numbers of patterns loaded into network, and visualize a bunch of key metrics for how well the network is performing as you increase the number of patterns. So I'll now walk you through just 3 of those experiments to give you a sense of why it seems that the capacity is higher for the oscillator version. So the first case, this is a case where we have very many patterns, or a very high dimension relative number of patterns. So this is on the order of 2,000 dimension and 20 patterns. And if we look at the convergence of the to the correct x factor, it would look the same for the y factor. It goes very quickly to the right solution. And then if we look at the energy function, so big caveat with the energy function, because the claim isn't that the resonator network has an energy function, but rather we look how well does it descend the Hopfield network energy function for each particular module. Does it end up descending it? And if it doesn't, then that's not a true energy function for the network. But my point here is that we can use that as a useful tracker of progress to understand the network computations, not necessarily that it's always making progress along this objective. So you can see that, as we'd expect, just as it's very quickly converging, the energy function is very quickly decreasing. The phase differences are all relatively aligned, indicating it's well synchronized. And in addition, the correlation across time, once it's converged, the yellow is around 1, so it's stayed very, very stable. Let's also look at a case where there's too many patterns loaded. So here, there's about 1,900 different patterns and still 2,000 dimension. And you can see the convergence is much worse. So compared to the other solutions, it's very unstable. I call this catastrophic unstable because it doesn't seem like it's found the right solution. The reason for this, it seems, is that even though it seems like it is initially descending the energy function, it fails to find the minimum solution. And in addition to that, it seems to be finding many, many spurious mixture states, which seem like they have high inner product, but don't correspond individually to one particular factor. And in addition to that, none of the solutions that it finds are particularly stable. So this is a regime where over time, it is locally correlated in time to its neighbor, but over time, it's largely moving around the state space and not converging to a particular solution. So in case 1, this is a case where both versions of the resonator network will succeed. Case 3 is a case where the oscillator version and the resonator will both fail. The key finding is actually case 2, which I call the benign unstable regime, where it seems is in the range where the oscillator network is succeeding and the discrete one is failing. So if we look at the convergence in this case, it's not to the true inner product. In fact, it's about 0.6 to 1 inner product, but it is head and shoulders closer to that inner product compared to any of the rest. And so if we're looking at the energy function, there's still some spurious mixtures, which is why it's not getting exactly to 1, but yet it's still able to be decoded because its inner product is much higher than for the rest, and so it can be decoded via simple thresholding rule. In addition to that, the phase differences, they're not completely aligned, but they're not completely unaligned either, so there still is some local structure in these phase differences. They're not completely uniform or completely random. And the correlation across time is remaining fairly stable. So it is the intuition to have here is that it's staying within the right base of attraction, even though it's swirling around it and not getting to the bottom. For many practical applications, this would be still quite worth it because you have to take into account this decoding threshold as it's not going to be as clearly separated, but still it's well separated between, in this case, 0.6 and approximately 0.1. And these are hard problems because you're working in a regime where the network has high capacity or as dealing with a higher capacity load. So this, I think, hopefully provides some insight into why the oscillator dynamics are working better. And I want to maybe pump this intuition one more way, which is in cases where the initialization might be set randomly or it might be set evenly across all factors. The most difficult step oftentimes in getting the network to converge is making progress when the estimate is very uncertain, very far away from the original solution. Because if you're close to the original solution, then you're only a few steps away. In these kinds of cases, you might have a sum of many terms which contribute noise. And if they interfere with each other in such a way that they're going in all sorts of different directions because of random initialization, then this might end up meaning that the amplitude of the eventual signal is close to zero, or by expectation is close to zero. But then, when using something like a thresholding, which is setting the amplitude back to one, what ends up happening might be that there's amplification of noise, in which the estimate, which was off by a bit, is going to be off by even more. And I think that this is part of the reason for why the limit cycles were observed in the original paper. Namely, that it seems that there's a lot of noise that's coming both from the crosstalk between different vectors, and then also from the estimates not being quite close to the solution. And so it seems that in this, what I'm calling the benign unstable case for the oscillator case, the actual or the discrete updates are in the catastrophic regime at an earlier point. So it seems that this second regime is really contributing to the key difference. Or I think that this is the main claim that I have that's supported by all the evidence and experiments that I've been running. So the next thing, so it works better. It has stronger empirical performance. That's cool. What about the cost to simulate it? It turns out that there are efficient simulations of this oscillator network model, and you can use this based off of advances from simulating ordinary differential equations with adaptive step sizes. So, of course, we have to acknowledge that if we were to just simulate the continuous time dynamics with something like forward Euler and so forth, then that might rapidly accumulate errors. And in addition to that, it would naively take many more iterations to converge compared to just the discrete update version because it is taking larger jumps in the search space. But it turns out that with these adaptive step size methods, if you look at the number of iterations that the network takes to converge, and just taking some number of iterations, checking if it's accurate, and then seeing how well it gets to 100% accuracy, the number of iterations is actually quite comparable. The caveat here is that the continuous methods are using fifth order or eighth order methods here. So what's involved in a step might be slightly different than what's involved in a resonator update network step. But the main point is that there are actually efficient simulations of this on CPU, and that just leverage out-of-the-box methods for simulating differential equations. And so what this is promising is that you can get these benefits of higher capacity in a way that is also able to be implemented efficiently, whether or not you have access to particular neuromorphic hardware or architectures. And one last bit to add on to this is that if you wanted to use these systems, not just for particular phasors, so any continuous value between 0 and 2 pi, but you also wanted to get them to converge to -1 or +1 or the qth roots of unity, so some set number of discrete states, there is a simple trick that you can use to get the continuous time dynamical system to settle to one of 2 points. That trick is borrowed from oscillator Ising machines, and it's called subharmonic injection locking. So the key thing is that Q is the number of roots of unity. So if you just have 2, then Q is 2. And so then that encourages the phase to either go to 0 or pi if Q is equal to 2, so that this term is set to 0. So then T squared is the time step. So this is an annealing schedule that's regulated by a time constant, tau. And in this case, in the figure that I'm showing you, the Q is set to 3, inspired by some previous work from Connor. And it turns out that, yeah, as you'd expect, so the different colors are for the X phases and the Y phases respectively, but all of them are returning to some discrete root of unity, the third roots of unity. And the reason why it looks like there's more than 3 is just because in the simulation, it's more efficient to do this with the unwrapped phase. Even though, because of the sine term, it's only the wrapped phase effectively that has an impact on the dynamics. So now with that, let's just turn to a application of the system. So this is building off of some work that I presented in the last VSA Online on computing with residue numbers and using resonator networks to tackle the subset sum problem. So just as a reminder for how this works, suppose we have some set of integers s, and we want to check if there's a subset s star of the set that sums to this target t. So in this case, I just have a set of 6 numbers. This target is 42, and 3, 17, and 22 are the solution or the subset that sum to this number, and there's no other subsets that would be a feasible solution that would equal this. So this is closely related to the knapsack problem in optimization, except that it demands equality as a particular solution. And the intuition for why it is NP hard is that the whole power set of S, which is exponential in the size of S, is a possible candidate for the solution to sum. So it's NP hard under mild conditions, such as when you have integers that are all non-negative, for example. So we can solve this subset sum by casting it at a vector factorization problem. And I think the key takeaway here is not just that the network is able to solve it, which is consistent with the work from the earlier paper, but also that it's gradually increasing its confidence aerodynamics over time. So you can see the clean separation between the variables that are included at the top and the variables that are excluded at the bottom. So the confidence is just the normalized difference in the inner products visualized on the left. And the other nice thing is that this is a pretty small problem, so the search space is 64, but this is with a dimension of only 50. And so I think that this ties nicely to some of the connections related to sketching and what is the dimension that is needed to efficiently solve some of these optimization problems. In that, even though you're going to need larger dimensions or larger constraints as your problem size grows, there are efficient solutions and ways of using randomization, whether in the codebook vectors or in randomized restarts, that are able to solve these types of problems efficiently. So this is just a proof of concept, and I think another key thing is that it's very interpretable as to when it's making progress or making convergence. So I think that in practice, it's been there's some difficulties in figuring out, okay, what are the right convergence criteria? When can we stop early? What would be sufficient statistics for that? But and part of that is because the dynamics often look a bit jumpy. We can look at plots for specific examples, but the animation that I showed earlier would be one such example, which makes it difficult to track progress and tell when is it going to converge or not. But here, the dynamics are evolving pretty smoothly over time, in part because it's a continuous time dynamical system, but also in part, I think, because there's not the hard resetting that's induced by these thresholding operations or normalizations that are happening after every time step. So just to sum up, and this is the last technical slide, which isn't even that technical, to be honest. I started off by introducing the ideas of binding by oscillations and binding by multiplications. And what I hope I've been able to convince you is that this is a concrete instance in which these two ideas function in a complementary manner to each other. So on the one hand, we've seen that the oscillatory dynamics are this continuous time relaxation of the system, with a bit of help from techniques from oscillator Ising machines, is able to improve the memory capacity. And we've dug into reasons for why that is the case. So it's not just an empirical result, but it's an empirical result that we can understand or get a grip on. And in addition to that, it's not just that it's an oscillatory system that is able to solve all these problems, but rather the fact that the resonator network functions as compositional associative memory that breaks down a very large search space into compact individual elements or components is able to be a much more efficient solution than a brute force search in trying to decompose or parse visual scenes or solve subset sum problems. And this allows new applications of oscillator networks that might not have been available if you're just using a oscillator network with some arbitrary connectivity pattern. And finally, I've shown you that it can be simulated efficiently. There's discretized phasors representations for solving discrete optimization problems, and it works well on subset sum. So the combination of possible hardware compatibility for potential oscillator systems that people are physically building, the higher transparency of the system in terms of being able to visualize the dynamics and understand the convergence, and the better capacity, I think are all in their own right compelling reasons to look into the system more and reasons why I'm excited to continue working on this topic. So with that, now you understand why the title and the color coding is the way that it is. So I want to thank the co-authors for this project, especially Connor, who did a lot of amazing work and insight onto higher order oscillator or higher order oscillator Ising machines, which inspired a lot of this work and helped a lot with yeah, some practical tips for helping the simulations, as well as Zayu, Marco, Dennis, and Bruno, and then yeah, the Redwood Center as a whole, and yeah, including yeah, all the amazing people that are working on VSA methods, and then the funding sources for supporting. I also wanted to mention the Fernstrom Fellowship was what allowed me to visit Sweden a couple of years ago, and so it was really helpful when I was able to visit yeah, Dmitry, Evgeny, and Dennis, and have some really like helpful discussions about associative memory there that I think are still they're still bouncing around my head, and I think they're yeah, source of inspiration to the work. Thank you all so much.
Thank you, Chris, very much. A great talk as always. So now it's time for discussion and questions. Maybe to as an icebreaker, so I have a couple of simple ones on my own.
Hmm.
This subset sum problem. So
Yes.
what is the behavior when the dictionary or code books do not contain exact numbers that sum up to the target?
Oh, that's a good question. So if there is no like right solution, then the convergence looks pretty
Pretty
um,
bad.
gibberish. Yeah, because there's nothing to converge to. Yeah.
Okay.
Yeah.
So it doesn't kind of converge to the closest, say, number.
Um, I think that raises an interesting question of whether that when that would be like a bug or a feature. So one like way of getting around or getting it to converge to a close feature is to add another codebook that lets you just add a arbitrary amount. So like say a Slack variable that goes from 0 to 5.
Mm.
And um, so I haven't done extensive evaluations of this. I'm just sharing the idea with you freely. But then the idea would be, okay, if something converges to 39, but you need an extra 3 to get there, then that extra variable would help it to converge. And then you could do a randomization procedure and then take the best solution, which ends up being, I think, quite on par with some method like randomization methods used for solving these problems anyway. Um, so
Mm.
that would be the way the easiest way of getting to that. The downside is that now it won't always converge to the optimal solution. Sometimes it'll depend on initialization.
Thank you, Chris. Another question. So you exemplified this work on the case with two code books. So basically two factors.
Yes.
Can you say or give an intuition how it behaves with more than two factors? And the
Oh,
convergence capacity is in terms of you know size of code books.
yes. So I think that so maybe I'll just say first that if you had more factors, then you just add another exponential term here. So if you had
Mm,
z, then it would be times this and then times z and so forth.
mm,
The general trend that I've observed when working with higher factors is that there also is an increase in capacity, but I think that the scaling laws are roughly the same. So it's not that it's increasing it by a significant amount, as you can see, like from going from the oscillator version or the baseline to the oscillator version. But it's not that the scaling like law curve is significantly steeper. The reason I think for that is that in the NURBS paper, we did some empirical analysis of the what the upper bound based off of the memory requirements should be. And the basic prediction there would be, yeah, as you add more factors, so you go from 2 to 3 to 4 factors, you take a hit in what the scaling or the dimension needs to be. So if your dimension is d and you have two factors, then the capacity scales about on the order of d squared. But if you have 3 factors, it's on the order of 4 thirds, and if it's 4 factors, it's on the order of 5 fourths. So it turns out that that's the upper bound from some like napkin math, and that if you actually look at what the empirical curves are, it's close to that. So for that reason, I wouldn't expect the oscillator to do like better in some like big O sense. But I think that the constants are important.
Mhm.
I hope that helps, yeah, with the intuition.
Yeah,
Yeah.
absolutely. So, other questions, please?
Oh, I see one in
Yeah,
the
yeah.
chat. So I'm just reading it out. Chris, do we convert existing vectors to the oscillator format for use? Trying to tie this into hardware. Um, I think that the easiest way of converting um, so the vectors into um, an oscillator format is you can either represent it as the complex number, or you can just work at it on in my experiments I work on it, for example, with the um, unwrapped phase value and then use the sign nonlinearity in order to yeah, deal with things just so I don't have to deal with wrapping when working through the experiments. Um, for particular hardware, I think I'm happy to chat more about what would be the like most efficient or performant implementation. I think that there might be multiple, but I wouldn't be immediately sure how it ties in with how you're thinking about things. But happy to chat more about it.
Ross and then Tony. So,
Beat you by a second, Tony. Um, Thanks for the talk, Chris. This question is really more about resonator networks in general than specifically this oscillator version. But I'm presuming that with your code books, where you have discrete values, they're essentially just randomly chosen discrete values, yes?
Yes, they're randomly chosen.
Okay. So then looking at those various regimes you're talking about, the benign and the catastrophic.
Yes.
I wonder whether, I mean, so yeah, we tend to choose things randomly just because we don't know anything else to do, and it's just sort of mathematically convenient for proofs and so on. But I'm thinking in real agents in the world that items in memory sort of probably compete in some evolutionary, some Darwinian sense for those items which get to survive over the over the course of the agent's life because they're useful for factorizations. So I'm wondering um, whether there'd be any mileage in, could you actually choose your the contents of your code book so that they're optimized to extend the useful regime of the
Yes.
network.
Um, Great question. So I think that you're absolutely right, by the way, that I like the random assumption is often a useful like null assumption, helpful for proofs and so forth. And then for from the like neuroscience context or thinking about, okay, where do the code books come from? Can you do better? Those are definitely like open questions. And I'm aware of some like folks, at the Redwood Center and otherwise, they can feel free to speak up if they would like, that are trying to work on like how to learn the code books in a principled manner, according to some particular objective function. Um, I guess the way I think about this is that there's both like, okay, the learning aspect of where do the code books come from, and which is not really addressed here. And then the inference step of once you have them, how to do that step efficiently. And I think that the real challenge is how to learn meaningful structure in a way that is not interfering with the inference, where the interference comes from crosstalk noise between the vectors. So, the deep learning solution to this sort of problem is to use nonlinearities like softmax in order to better separate these individual vectors. I think that there's other possible like approaches, like done some work like trying to explore like sparse coding as a possible solution for this separation. Yeah, Paxson might have some more to say about. I'm not trying to put anybody on the spot, but I'm just like I think that it's a really good question, and I think that there's a lot of interesting opportunities there.
Okay, thanks very much for that. Cheers.
Mhm. Cheers.
Tony, please.
Yeah, yeah. Thanks for the talk, Chris. It's really interesting. So Can you flip to that slide for the subset sum problem? I'm just trying to understand how you set the problem up here.
Yes.
So where does T come from? Does it like have the solution already built into it? Is it like the product of the vectors for 3 and 17 and 22?
Yeah, good question. So the way it's set up is it's quite similar to the methods for like as you're using for trajectory association or like as we've later used for like integer factorization and so forth, where the idea is you start off with some random base vector, which is yeah, of random phasors, and then if you pick them from the uniform distribution, then that'll ensure that different integers are set to
Yeah,
orthogonal vector positions. But it still has the algebraic property that if you
yeah,
bind two vectors, it adds them together.
yeah.
So what
Okay.
is done here is just to create the base vector, exponentiate it, which works in this case because it's an integer to 42, and then set each of these vectors to be either an identity vector, so adding 0, or the base vector for 3, and the same for each of these. So now these are all like micro code books where there's just two possible solutions.
Okay. Okay. So if T was 25,
Hmm.
there's two ways of getting 25. This is some out of here that I see. 3 plus
Yeah,
22 and 8 plus 17. So you're saying that it would actually work both ways because you're
it
doing
could
it by
converge to either
construction.
solution.
Yeah, yeah, yeah. Okay, I get it. Yeah, yeah. So yes, yes, that makes sense now. I understand what you're doing. Okay, okay, cool. Thanks.
Cool. Thanks for the question, Tony.
All right, let's see if we have more questions. Maybe I don't know, kind of concluding, if you wish, yeah, question. So, how do you plan to continue with this research line? So, what was kind of most promising
Right.
developments?
I think that the most straightforward things are to scale up some of the experiments that were in the original workshop paper, to just uh, cross all the T's and dot all the I's in terms of understanding, yeah, the scaling and capacity and so forth. Like, as in, those are not in the paper, but they're sort of things that I've been running. Just yeah, on my own and haven't yeah, written up or published yet. I think that the other aspect that are interesting. So the way I see it is there's the what does the algorithm contribute side, and then there are the connections to neuroscience, and then the connections to hardware. So as far as the connections to neuroscience go, I think that the interesting thing is okay. I started off by introducing what are the possible connections of these associative memory models to hippocampus, and then what might be for the possible oscillations we see in hippocampus. What is the computational function? There's a lot of ink spilled on these topics, but I think that the memory capacity angle possibly adds some fresh new perspective into that question. And then as far as how to like implement this with like physical computing systems and so forth. So as you all know, I'm not actively working on the like hardware implementation side myself, but was recently at a conference hosted by the national labs in the US, where they're talking about some implementations of tractor networks with oscillatory circuit components. I think that that's one line of work. The oscillator Ising machines are another line of work. And I think just convincing someone, hey, we have a good algorithm for combinatorial optimization. It works well on different tasks compared to things that you've like thought about. And it would be really useful. And I mean, also like I realize Marco and Kaya are talking next week about hardware implementations, and I mean, I've been kind of thinking in the same space of like, yeah, where like modular arithmetic and these principles can play a role. So I mean, given that that's the next like VSA online talk, I would almost like even defer to them on what the
Mhm.
interesting frontiers
Yeah.
on that last front are. Yeah.
Absolutely. All right. So I give you a last chance for the audience to ask questions. Oh, so
Yeah.
we have back Tony and Ross. Okay,
Yes.
Tony,
really good. So,
Okay. Can you flip back to your slide with the digits on the screen? You had like
Yeah.
5 different digits on the screen. Yeah, the one prior to that, I guess, where you had yeah, that one. So this, I mean, this looks like it's potentially really powerful that you can, I mean, break down the different things that are present and represent things about them. And have 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 you seen people try using this kind of thing in any deep networks like transformers or other networks that are working with images? And one of the reasons I ask is that before, when I was working at Google, I was using the Gemini networks to try to understand scenes, to understand GUIs. And one of the things that I was observing was that they were really bad at keeping track at what was where and what was associated with what. It was just mixing everything up. I gave it like, scenes to analyze, like the arc AGI experiments, and simple ones where there was like circles and squares, just on a 32 by 32 grid with 10 different colors. And I'd ask it, how many circles are there and where are they? And it would just hallucinate half the time. It was amazingly bad. And it would totally mix things up and not doing the kind of binding that you're showing
Yeah.
can be done here. So I'm asking, are you aware of any work where people have taken these ideas and tried to put them into networks that are working at scale on interesting problems of scene analysis?
Do you mean with resonator networks specifically, Tony, or
Well,
more
just
generally? Yeah.
yeah, more generally, like just using these binding ideas. Could be resonator networks, or it could be more generally.
Yeah. So I recall like a VSA Online talk from some of the folks at like IBM who were like working on some things with like deep learning front end and VSA back end or some other combination of things. I'm not yeah, going I don't want to summarize too much
Yeah,
of that because I feel like the talk will do a better job than
sure.
I would try if I did now. One interesting line that I think is like really interesting from the oscillator front and associative memory is there's been some group from like Lyle Muller, yeah, in Canada and like others to think about like ways of working with like these oscillatory neural systems and then trying to tie them into things, for example, like state space models or other like recurrent neural networks for solving tasks like image segmentation. So I guess it's more like a computational unit within like a like deeper architecture. Um, or like the Miata work is not like VSA stuff specifically, but it's more on the oscillator side. I'm trying to think with like VSA things. I recall like Paul Smolinski's group had some work where they're trying to add in some of the like TPR primitives into transformers, which you may be already aware of.
Yep.
Like I think that the tricky thing is that like what the best way of combining the VSA primitives with like existing deep architectures are is kind of an open question to me because I want to preserve the transparency of VSA operations and have an understanding for the system, and I don't want that to get lost when it gets like merged with the deep learning bus. Um, so I struggle
Yep.
with the question too. Yeah.
Yep. Okay. Thanks.
Maybe I'll just add a thing to that, which is that if you think on the deep learning side, the closest thing I can think of doing something like this is Jeff Hinton's capsules network. So, that's very much incorporated in a learning framework. And you can sort of loosely think of what they're trying to do in capsules is unbinding the transformation from the shape of the object. So they have this kind of iterative algorithm that has to solve this dynamic routing problem, which doesn't map one to one onto this, but basically I think the core idea is very similar. Um, and interestingly, that work, as you probably know, Tony, of Jeff's, I sort of see the intellectual roots of that going back to his work in the 1980s with Kevin Lang, and his Ishkai paper on factorizing, literally, taking like an image of digits and shapes and factorizing it into transformation and shape. And this is kind of, in my view, kind of a more efficient way of doing that. Going into the VSA framework really kind of helps you see how to get that kind of system to work robustly.
Great, thanks.
Ross?
Chris, could you go back to the slide where you had the distributions of phase differences, please?
Yes.
Okay, and I think there was some other, yeah. And so at what point in time are those phase differences measured?
Oh, this is at the end state, or the
Right.
end state of the simulation. Yeah.
Yeah, end of the simulation. Okay.
Yeah.
And so basically the units of observation there are phase difference between the x, or the estimated x and the true x on an element-wise
Correct.
basis. Would that be right? Yeah. Okay.
Yes. Yeah.
Okay, so in that, looking at, say, the benign unstable and the catastrophic unstable regimes, if we were to concentrate on a single hypervector element, what would the phase difference for that look like over time?
Oh, so how would the phase differences like drift or change over time?
Yeah. I'm presuming, because earlier on you're talking about limit cycles, so I'm presuming that an individual element would would basically follow some recurring trajectory of difference.
Yeah. Um, so that's a really interesting question because I have seen it for the population level, but that doesn't resolve what it looks like for the individual units. And
Yeah,
um, why don't I look into that and get back to you about that?
yeah.
I'm
I mean,
interested in that too.
I'd be interested to know if you're in that benign regime. Are there some elements which converge to a fixed phase difference, and some vector elements, which go cycling through a range of different phase differences?
Hmm.
Chris, why
Yeah,
isn't
me
it
too.
zero? Why isn't it phase difference zero? Why is
Oh,
it two?
that's because like it's the equivalent of in the resonator problem, like you could converge to minus x and minus y because they both go to s and they have the same like yeah norm of the inner product. So if you have x star plus like every vector element is shifted by pi over 2 and every vector element here is shifted by minus pi over 2, then that'll lead to a constant phase difference. But the if you take the inner products, now they're complex numbers, and so the complex valued inner product, the amplitude is going to be the same, even though it's the shifted by a constant amount, but the phase will be different. Um, sorry,
Yeah.
I hope that makes sense.
So in fact, rather than reporting the phase difference, it might make more sense to report that inner product on an element-wise basis, because that's the quantity you care about, and the inner product is just a sum over elements anyway.
That's true. Yeah.
Yeah.
Wait, is it pi over two then? Or is it just some arbitrary number?
It can be an arbitrary number because any of those, like, if you, it's just like a fact of using the product of two complex phasors, right? So if you shift the phi x by a certain phase shift, and then you shift phi y by the opposite phase shift, then it'll be it, it will still multiply to s, but it'll just be off by a particular number. If you discretize the phasors so that they can only go to -1 or +1, then it's just the like classic like binary resonator thing where it either the shift is either 0 or pi, which just corresponds to yeah -x and -y or positive x and positive y. Um,
Thanks very much for that, Chris. I'll be interested to hear if you follow up on that. That's interesting to me as well.
yeah,
Thanks.
absolutely.
Maybe to conclude, if you can attend the one question from Tyler in the chat. So,
Yes, I'll be happy to. I realize we're at the hour, but I'm so glad we had the extended time for discussion. And really, yeah, grateful for, yeah, all the questions and back and forth. So, okay, as I understand the question, so let me be clear about the method for converting in software. So the method for converting in software are using smart like adaptive step size solver methods for simulating ODEs. And so if you had a physical system, I think that would not be compatible with that ODE simulation because you'd actually be instantiating the dynamical system. So I think that you wouldn't stack that with the hardware advantage. But the hope is that if you had a hardware system that can implement yeah, these weights or these interactions and whose dynamics are working on the phase variables. Now, the phase you could represent as a complex number, or you could just treat as an unwrapped phase and something like a real value or something like that with a particular range. Then I don't think you need to worry too much about the conversion properties. So the advantages you get from the hardware are going to depend more on the particular implementation. But I think that the hope is that it like points to new implementations that you might not get just by or that might not be suggested just by like the sign implementation. In fact, like that's the whole like idea from going from Ising machines to oscillator Ising machines. I think you can go from resonator networks to oscillator resonator networks.
all right, looks like we have approached the end of the seminar. So thanks a lot, Chris, for the great presentation, and thank you all for good discussion. So it remains to say that I see you in 2 weeks from now. So we have a great talk by Marco and Caio from Italy. So stay tuned and have a great time, everybody. Bye bye.
Okay. Thank you all so much. Bye.